In this video, we're going to look at solving equations that are in quadratic form. These are equations that can be written as quadratics using a form of substitution. So looking at our first example, we have the quantity 4x plus 3 squared minus 7 times the quantity 4x plus 3 plus 12 equals 0. We're going to use a process called U substitution. This is a very common type of substitution with the letter U. You could use whatever variable you wanted. The only variable you would want to avoid is x, since that's the variable in our original equation. So we're going to let U equal 4x plus 3. And if I substitute that back into my original equation, that means I've got U squared minus 7U plus 12 equals 0. And now that we've got this U substituted in, this looks like a very straightforward quadratic that's going to be pretty easy to set up and solve by factoring. You have to be very careful, though, to maintain that we're using U. Sometimes we get into autopilot and want to go back to X, so just be cautious there. So factoring U squared minus 7U plus 12, my first terms are going to be U, and then my next two terms are going to be factors of 12 that sum to -7, so it's going to be -3 and -4. And when we solve this, we're going to get that U equals 3 or U equals 4. Now we back substitute to figure out what our value of X is. So instead of U, we have 4x plus 3 equals 3, or 4x plus 3 equals 4. Solving the first equation, we have 4x equals 0, x equals 0. 4x plus 3 equals 4. We're going to subtract 3. We get 4x equals 1. X is equal to 1/4. X to the fourth minus 7x squared plus 12. It's important to remember that x to the fourth is x squared minus 7x squared plus 12 equals 0. So we're going to let U equal the quantity x squared. Substituting this in, we have U squared minus 7U plus 12 equals 0. And this is going to be the same factors we had above. So this is going to be U minus 3, U minus 4. We can solve that U is equal to 3 or U is equal to 4. And now we want to back substitute in what U represents. This is x squared. Now, when we're solving these equations and we're taking the square root, remember to add the plus or minus. So we get x is equal to plus or minus the square root of 3. Or x is equal to plus or minus 2. So this equation actually has 4 solutions. X to the 2/3 power plus 2 times x to the 1/3 power equals -1. I have a comment here just recalling the relationship between rational exponents and radicals, but well, no, let's keep it like that. So we're going to use this property. There's another property we could have used. We could have just used the power rule of exponents. So x to the 2/3 is the same as the cube root of x being squared plus x to the 1/3 is the cube root of x equals -1. So we're going to let U equal the cube root of x. So this becomes U squared plus 2U equals -1. Setting this equal to 0, U squared plus 2U plus 1 equals 0. We can factor this. It's going to be U plus 1 times U plus 1. Since both of these factors are the same, we don't need to solve both of them. We can see that u is equal to -1. And we're back substituting u is equal to the cube root of x equals -1. To undo the cube root of x, we're going to cube both sides. We get x is equal to -1. Now, since this equation did start as a radical equation, if you recall from our previous video, we do want to check our solutions for a radical equation. So if we were to check this, and I'm going to use the radical form of my equation instead of my rational exponents. We've got the cube root of -1 being squared plus 2 times the cube root of -1 equals -1. The cube root of -1 is -1. So when we square -1, we're going to get +1 plus 2 times the cube root of -1 is -1 equals -1. This is going to be 1 minus 2 or -1. And that is true. Now, I'm showing that we checked this simply because we've generalized the naming of our radical equations. When our index is odd, we actually don't need to check our solutions, because with an odd index, we don't end up having potential extraneous solutions. Extraneous solutions arise when we're solving an original equation that has some sort of domain restriction. So a cube root function, the domain is all real numbers, unlike a square root function where we do have that restricted domain, which is why we have to check for those extraneous solutions. And I want to go ahead and show this problem just set up a different way, because it was initially where my head went to when I saw this problem during the video, but looking at my notes, I solved it this way. So I want to illustrate both methods, just depending on what you're thinking at the given moment. So our equation was x to the 2/3 plus 2x to the 1/3 equals -1. And what I was thinking initially was x to the 2/3 is the same as x to the 1/3 squared, because power to a power, we multiply those exponents, plus 2 times x to the 1/3 equals -1. So then here I would say, let u equal x to the 1/3 power, and we would get that u squared plus 2u equals -1. Thinking about u being x to the 1/3, that is the same as the cube root of x. So we haven't changed it. It's just thinking about that problem a little differently.